Okay, now let's look at the harmonic potential. So now I want to be a little bit careful to distinguish this potential from the Coulomb potential that we just talked about. So we're really talking about now two atoms which share a bond, okay? And again, as I mentioned before, this could be, oxygen atom, H atom, could be carbon atom, oxygen atom, could be H atom, F atom, could be, many, many different atoms. Could actually be more complicated molecules too that have, and you could think about all of the different bonded pairs in a polyatomic atom, and you could still think about the same harmonic potential. But now there's a difference, right? So the atom isn't just simply a single charged particle like the electron and the proton are. The hydrogen has one proton and one electron. That's the entire atom. The oxygen atom has 8 protons and 8 electrons. And so now we have those two atoms interacting through a very complicated set of, fundamental interactions that give rise to the chemical bond. And sort of this average interaction after, that accounts for all of those different microscopic, Coulombic interactions between all the charges, etc. We model with a potential called the harmonic potential. Okay. So the harmonic potential is really sweeping an awful lot of detail under the rug. But nevertheless, the idea is kind of the same. There's a separation between the oxygen and the hydrogen atoms, and we call that separation R. Okay. So again, we can write down a form for this potential, right? A mathematical expression, which I'm going to call V of R, is equal to 1/2 K R squared. Okay, and actually, just like before, let's be a little bit careful to color code what is a variable and what is not. Okay, so in this case, the variable is R, right? The separation. And K, it's not a variable, K is a constant. It's called the force constant. Okay. Why is it called the force constant? Okay, well, let's take our same idea as before. Let's use our expression that the force as a function of separation is equal to the negative derivative with respect to R of V of R, right? Okay, and now, right, so how do we do this operation? Negative d dr of 1/2 K R squared. Okay. So I need to again pull down this exponent, multiply everything by this exponent, and reduce the value of this exponent by 1 to take my derivative. And that is going to give me and multiply the whole thing by -1. It's going to give me minus K times R. That's my force. Okay? So F of R for the harmonic potential is minus KR. And there's a name for this. This is a particular expression called Hooke's law. Okay, and basically Hooke's law applies to a lot of different ideal systems, sometimes called ideal springs. The idea is basically the force not just the force, because again, the force has a sign, but the magnitude of the force is linearly proportional to displacement. Okay, that's a kind of in-word statement of Hooke's law. So let's draw these two potentials. Just like we did before. Let me give myself some room again. Let's draw the potential and the force. That's what I meant. Okay, so give myself a little coordinate axis here. In this case, R has a slightly different interpretation. Okay. R is really the separation between H and O relative to the equilibrium separation. And the equilibrium separation is typically some relatively small positive value. But what we've basically done is we sort of shifted, we kind of shifted our coordinate system to the left by the equilibrium separation. So in the way I've written this expression, the minimum of the potential occurs at R equals 0, right? And at R equals 0, we don't actually mean when H and O are right on top of each other. We mean that when when we are at the equilibrium separation, so then the difference between the actual separation and the equilibrium separation is 0. So a little bit confusing. If that point is confusing to you, we can talk about it in class, and I can also make a modification to this expression so that it's not centered at 0, so that it is actually centered at the equilibrium position. That's not a problem. Okay. All right. But if it's centered at 0, the math is just a little bit cleaner. All right. So this is V of R. Okay. So you can see it's a parabola. Okay. And what this tells you is if I pull my atoms farther apart relative to the equilibrium, the potential energy goes up. And if I push my atoms closer together relative to the separation, the potential goes up, right? So having R greater than 0 means pulling them further away than the equilibrium, and having R less than 0 means pushing them closer together than the equilibrium. Okay. Now, let's also plot the Hooke's law of force. Okay. So the Hooke's law of force, let me do in red. And it's just the derivative of this parabola multiplied by -1. So it goes to 0 also at r equals 0. For r smaller than 0, right, when r is negative, I'm multiplying by -k, and k is some positive number. So when r is less than 0, I've got a positive force. When r is greater than 0, I've got a negative force. Okay, so basically, the Hooke's law of force looks like this red line. Right? What's the slope of this red line? The slope is k. And again, can we make an argument that the derivative multiplied by -1 of the potential gives me a proper force? So what happens when I push the atoms closer together than the equilibrium? The force is positive. So the force being positive means which direction is it pushing? It's pushing in the positive r direction, which means it's pushing in the direction of lengthening r, right? Getting back to the equilibrium. If I make the bond shorter than the equilibrium, the force pushes in the opposite direction, right? Back to equilibrium. If I stretch beyond equilibrium, the force becomes negative, which means that the force is pointing to the -r, restoring you back to the equilibrium. So the negative of the derivative of the potential seems to make sense for the direction of the force. Okay. The other thing that I'll say is that at the point where the potential is minimum, that's when the force is exactly equal to 0. So that idea is very important, right? Force goes to 0 at the equilibrium separation, which is where potential is a minimum. This isn't really something that we could realize with the Coulomb potential, right? The Coulomb potential continued to decrease towards negative infinity. It never turned around, right? So there wasn't really a minimum in the Coulomb potential, right? It continued to decrease towards negative infinity without bound. So the harmonic potential is a bit different, right? It actually has a minimum. It has a place where the force vanishes at the equilibrium. Okay, and our final potential that we'll see, the Lennard-Jones potential, also has an equilibrium position and a position where the force will vanish.